Hello, today we're going to look at this equation, Q equals mc delta T, a significant equation for doing our calorimetry calculations in chemistry. Sometimes people remember this as Q equals MCAT, not actually an A, that's a delta sign, but close enough, and it's helpful for remembering this. So let me write a few things down near this equation that should serve as reminders for us. Whenever you see Q in this equation, think of heat. Sometimes we use the term energy. Those are interchangeable here, heat or energy. This is going to be measured in joules for this equation. Recall also that we've talked about heat being measured in calories, and there's a useful conversion that lets us convert from calories to joules. The M in this equation stands for mass measured in grams. The delta T, so that triangle and the T together, mean the change in temperature. All right, so what about that last variable? The C in this equation stands for specific heat capacity. So the specific heat capacity is a constant. Depending on the substance, there will be a certain value that tells you how well that substance can absorb or hold on to energy that is transferred to it. You'll notice to the right there's a table that shows a bunch of specific heat capacities. And notice at the top of the list is water, which has a very good ability to hold or absorb energy. So when heat is added to it, the temperature doesn't change much. Notice that all the other substances on this list are metals, and that they have much lower specific heat capacities. In other words, you add some heat to a metal and the temperature changes dramatically. All right, let's use this equation and the specific heats to solve a couple calculations. Question number 1 here, how much energy is required to heat 2.4 kilograms of water from 46 to 100 degrees Celsius? I'm going to write down a few variables as we work here. The first one is the mass. So the mass is given as 2.4 kilograms, but when we use our values for this equation, we want mass to be in grams. So let me just get this out of the way right here. We'll turn those kilograms into grams. You can do that using a useful conversion. If you haven't memorized it, up in the table, you'll notice that we are reminded a kilogram is equivalent to 1,000 grams. So if I multiply those, the grams cancel out, and we're left with 2,400 grams here. So the next value that I'm going to write down is, I'm actually going to write delta T. Let me calculate that though. So up above it says that the value for delta T is equal to the final minus the initial temperature. So let's calculate delta T. 100 minus 46, which is 54 degrees Celsius. The sign is significant with delta T. So a positive sign tells us the temperature is increasing, like in this case. If we had reversed the order of those numbers and done this calculation, we would have gotten minus 54, which tells us a negative value that the temperature is going down. All right, let me write one other number down. Because they told me that this substance is water, then I'm going to use this first specific heat capacity, 4.18, in my calculation. Notice the units include joules, grams, and degrees Celsius. It's joules per gram degree Celsius. So then we put all this together in our calorimetry equation, Q equals MCAT. So Q will equal 2,400 grams times 4.18 joules per gram degree Celsius times 54 degrees Celsius, our temperature change. And we calculate this, 2400 times 4.18 times 54 is equal to 541,728. Notice the units in this. So the grams crossed out and the degrees Celsius also. So I'll write the units as joules. Now this number, we need to do some rounding. Notice in my calculation, I only had 2 sig figs in that mass measurement. I had 3 in the constant that we used, but I only had 2 sig figs in the temperature change. So my answer should have 2 significant digits as well. Let's call that 540,000 joules. Sometimes you'll see this written as 540 kilojoules. All right, that's a simple calorimetry calculation where we were looking for the energy or the heat. Check out this next example. In number 2, we've got a solid gold ring with a mass of 15.2 grams. Let's write that number down. M equals 15.2. Is heated with 184 joules of heat. Write that down as Q. Q equals 185 joules. The ring's initial temperature is 22.4 degrees Celsius. What will be the final temperature? Well, there's actually one other number that I can write down here. They told me that the ring was made of gold, so I can look up the value for the specific heat capacity of gold, which is 0.129. And that's joules per gram degree Celsius. All right, this time when I solve this problem, Q equals mc delta T, I'm going to write delta T a little differently. Remember from our useful equations here that delta T actually means T final minus T initial. And so I'm going to put it in that way, T final minus T initial. And let's plug in some numbers, 185 joules for Q, 15.2 grams for M. For C, we're using 0.129 joules per gram degree Celsius. For T initial, well, T final is what we're solving, and T initial is 22.4. All right, so I'm going to do this problem this way. I'm going to say TF minus 22.4 degrees Celsius is equal to 185 joules divided by, so remember your algebra here, we're just going to divide both sides by 15.2 grams and by 0.129 joules per gram degree Celsius. Clear some space here. So I had a 15.2. I had a 15.2 grams and a 0.129 joules per gram degree Celsius. The 15.2s and the 0.129s canceled out, and that's how I ended up with TF minus 22.4 degrees Celsius on the right side. Again, I'm going to write this out a little bit neater. TF minus 22.4. And on the left side, I ended up with 185 joules divided by 15.2 grams, also divided by 0.129 joules per gram degree Celsius. The joules in this cancel. The grams in this cancel. And so the units for my answer are going to be 1 over degrees Celsius, or just degrees Celsius. The number comes out to 185 divided by 15.2 divided by 0.129. So 94.3. That's equal to TF minus 22.4. So at this point, I'm going to solve for TF by adding 22.4 to both sides. So now I can see that TF will equal 22.4 plus 94.3. 22.4 plus 94.3. It looks like I got 116.7 degrees Celsius. That is the final temperature. All right, let's solve one more of these problems. So for my third example, again, we've got several numbers that come up in this problem. A good approach when you're solving these is to make a list of those. When 405 calories of heat are transferred, that sounds like the value for Q. Notice they gave it to us in calories, and that's not going to work. Again, when we use any of the values from this table, they're supposed to be in joules per gram degree Celsius. So there's a conversion that I like to do right off the bat here that turns calories into joules. If you've forgotten the conversion factors, you can always look those up. It says that a calorie is 4.18 joules. 1 calorie, 4.18 joules. And so 405 calories is kind of like saying 1,692.9 joules. That is the value for Q. The value for M is 87.2 grams. So in this problem, the metal is unknown. I read on and see that the temperature change can be calculated here, delta T. They gave me two temperatures. The final temperature, which was, remember that's the TF in this equation, 68.5. Subtract from that the initial temperature, which was 18.2. The temperature change for this metal was 50.3 degrees Celsius. All right, notice I've got Q, I've got M, I've got delta T. The only number I don't know is the value for C. So let's solve this. Q equals MC delta T. This time, before I plug any numbers in, let's clean up our equation. Let's solve our equation for C. Well, it's easy to do without all these numbers written in. I'm just going to divide both sides by delta T. I'm going to divide both sides by M. And rewrite my equation in terms of C. So C equals Q over M times delta T. All right, so C will equal 1,692.9 joules divided by 87.2 grams, also divided by 50.3 degrees Celsius. Notice that our units, they do not cancel. we're going to have all of these units in our final answer, joules over grams and degrees Celsius, which is great. Those are the units for calculating specific heat capacity. Punching in 1692.9 divided by 87.2 divided by 50.3, writing my answer as 0.386 if I round this to 3 sig figs, 0.386. That is the value for C. And that should let me identify this unknown metal. I go up to the table and find something that has a specific heat capacity close, might not come out exact, but copper's is given as 0.385. That's pretty close to 0.386. Sounds like our unknown metal here was copper based on the specific heat capacity. All right, those are 3 examples of how we can use this new equation, Q equals mc delta T, to solve a variety of calorimetry problems in chemistry. Good luck as you solve your problems.